I hope there are some people connected, and we thank them to be connected. So today is another session of the Moroccan Center of Game Theory Seminar, and we have the pleasure to have two presenters today, coming from the far America. Omar Housni, who is originated from Morocco, and after being graduated from the École Polytechnique in France, he did his PhD at MIT, at Columbia University in operations research, and now he's assistant professor at Cornell University. And it's a big pleasure to have him presenting two-sided assortment optimization. And just for people that are connected, don't quit. After we'll have a second seminar with Jose Correa, who will be presenting some work on poverty inequalities. And the floor is yours.
Hello, everyone. Great pleasure to be here. Thank you so much, Rida, for the presentation, and thank you for hosting me at the Moroccan Center for Game Theory. I've been to this campus many times, and I've always enjoyed coming here and interacting with people. So today I will be talking about some recent work that I've done on two-sided assortment optimization. This is a joint work with Alfredo Torrico, who was at Cornell, and now he just started, I should have updated the affiliation, he just started as a faculty at USC, University of Southern California. And my PhD student at Cornell, Elise Enbel. I'm looking for the clicker. Where did I left the clicker? Oh, it's here in my pocket. Cool. So please, throughout the talk, I'm gonna, give an overview of assortment optimization, two-sided assortment optimization, and then go into a bit more details. Feel free to stop me at any time if you have any questions, please. Okay. So before even talking about two-sided assortment optimization, what is assortment optimization? So this is a field, I would say, at the intersection of optimization, of revenue management, and operations research in general, that was mainly motivated by e-commerce application, where think about a decision maker, like a platform, that needs to decide what's the selection of product to offer to their customers. For instance, like Amazon have access to a large number of products, but they can only offer a subset of those products to the customers. So the subset of the product is what we would call the assortment of the assortment of product. And in order to decide what assortment to offer to the customer, the platform needs to understand the preferences of the customer. And these preferences are typically captured by a discrete choice model. So there has been a large body of work on choice modeling, on how to capture customer preferences. So once you have a good understanding of customer preferences and you estimate your choice model, so the choice model is a mathematical model that will give you the probability that a customer will select a product if you offer an assortment S. So typically, this is the probability that you will learn from the choice model. It's what is the probability that customer will choose a product I if you offer assortment S. And I want to mention something here important, is that this probability actually depends on the assortment because of the effect of substitution. Right, so a product might have a high purchase probability, but if you add another competitor next to it, that probability might drop. So it is important to notice that the purchase probability depends on the assortment. And the optimization problem, so you need to find a subset out of a universe that maximizes, let's say, the expected revenue. So expected revenue that you would collect from the assortment is a summation over all the product that you have in this assortment, the revenue of the product times the purchase probability. That's what you will get in expectation. Yes? Yeah, so the simple model, we think about just a monopolist platform. There is no competition. There is a lot of papers on competition in assortment optimization. Happy to talk about that as well. So I'm starting with a very simple model here. Yeah, so this is the typical, I would say, assortment. This is the most basic assortment optimization problem that you will find on textbook. that we teach to students, and depending on this probability, this problem might be simple to solve. You know, you can under some choice models, you can solve it in polynomial time. Under some other choice models, it might be NP hard, and there's a large body of literature in trying to design algorithms and approximation algorithms for this problem. But there is a large body of work, I would say, over the last 20 years on this. Alex, yes. So again, yeah, so this is the unconstrained problem, where you can think about like you optimize over all subsets. Even this problem is not trivial, because it's not clear whether you want to offer everything because of substitution, or you just want to offer a subset. There is also the constraint problem, where you add constraints on S. It could be a cardinality constraint, where you fix a size. It could be like some capacity constraint, where there is a weight for each product, or some matrix weight constraints. Yeah, and yeah, this is a well understood problem. I've seen there was another hand, yes. Yeah, so again, that's another line of research. So in the most basic, there is some echo. Can you please mute yourself? Okay, cool. So good question. Yes. So in the basic assortment problem, the customer is gonna buy here at most one product, a single product, or might also go to the no purchase option. There is also a line of literature that's called multi-purchase assortment optimization, where you go and you buy multiple products, and there are choice models that would capture that. Yeah. So this is just an overview of assortment optimization. This is not what I'm gonna talk about. This has been studied well over, I would say, the last 20, 30 years. What I want to talk about today is two-sided assortment optimization. So let me motivate what I mean by two-sided assortment optimization. So in the first example that I've given you, there is only a choice from one side, meaning the customer chooses the product. And once that choice is made, if the product is available, then the customer will get the product. The product doesn't choose the customers in some sense. Recently, there has been a lot of interest into this, what we call two-sided choice platforms, where there is choice on both sides. So here we're not gonna talk about a customer and the product, but we're gonna talk about, in general, about agents. So you have a two-sided market where you have agents on both sides, and they have choice over each other. For instance, on dating app, right? So you have a market with two sides, and every agent has preferences over the other side. That's also like the case, in some other application, like in outsourcing, like in Upwork, you have like freelancers and customers. So the customers arrive on the platform, right? They've seen they want some task to be done, and they've seen some freelancers. They might choose to contact one of them, and freelancer also gets requests, many requests perhaps, and they will choose like which project to work. So there is choice on both sides, and other example can be seen in accommodation, in carpooling. So here the platforms, they decide what to display to the agents. So they control the assortment. They might not control the matching directly, what's the final assignment, but they might control what to display to the agent. And the problem of deciding what to display to the agent is what we call the two-sided assortment optimizations. The word two-sided is because there is choice on both sides. So, and why do we want to, we get directly here? Yes. Why we would like basically to decide what to display? Because of the phenomena of choice congestion. So some popular options might receive a lot of requests, but if you display the assortment in some smart way, then you might avoid choice congestion and basically generate more matches if you're thinking about the objective function to maximize the expected number of matches. So here in these two-sided platforms, as I said, like in order to get a match, both sides must agree, must choose each other in order to generate a match. And the dynamics of the problem, they really depends on the design of the platform. So you can think about some design where one side starts before the other side respond. For instance, in like accommodation, like at Airbnb, like the customer is the one reaching to the host, and then the host might approve. In some other places, there is no two-sided, but like the first model of Airbnb, and it's still the case in many accommodation platforms, is that there might be an approval from the other side as well. So in that case, I just want to emphasize that the customers reach out to the supplier. In some dating app, like Bumble, only women can do the first match, and then the man will respond. I always give that as an example to my students because they know it very well. In some other dating app, any site can start the matching process. It could be done statically, like simultaneously. It could be done sequentially in the sense that the platforms observe the choice before deciding the assortment for the next agent. But so here from this overview, like there are two problems that we can identify here. So one is how user interacts. So like what's a good design for the platform? And then number two is like what they see. That's the optimization problem. What's the assortment? How the platform should decide the assortment to display to the customer. Any question about the motivation before I get into the technical framework? Very good question. So the first line of this work is not thinking about revenue, just thinking about the number of matches. So you want to maximize expected number of matches. We do have as well a recent paper that is focusing on revenue. So in that case, you could think about like if a pair a match that would generate some revenue for the platform. So if this freelancer is matched with this project, like there is some commission for the platforms, and the goal of the platform would be to maximize expected revenue. Just think about in one case, we have a bipartite graph with that is unweighted, and in the revenue maximization, each edge on your bipartite graph might have some weight.
That's very interesting because I think, again, I saw some relevant papers. Whenever you try to maximize the expected number of matches, it's a different concept compared to stability, for example. So stable location do not maximize the number of matches.
Yeah, so
In the sense, there will be interesting new objectives.
Exactly, and here we're not going to talk about stable matching because we are not given a list of preferences. So in stable matching, you have a list of preferences you need, to generate a stable matching with no blocking pair. Here, the preferences are captured by a choice model, and the choice model will give you the probability of choosing an option given the assortment. So there is, it's not captured by just a list, but it's captured by a function, a set function. Yeah. Sure. All right, so let's get into the mathematical framework. So I'm gonna start with a simple model. So here we're gonna think about a market with two sides. I will call them customers and suppliers. Okay, so on the left side I have customers, on the right side I have suppliers. It's a bipartite graph. And as I said, like each customer will have preferences over suppliers that will be captured by the discrete choice model. So what is the discrete choice model will give me? So if you basically offer an assortment S, then each customer I will choose supplier J with probability phi ij given S. Okay? So, and might also choose the no purchase with probability phi I0 S. No purchase meaning the customer is not happy with any of the options and might just leave the market. Similarly, on the other side, for each supplier, there is a choice model. Phi j I c is the probability that supplier J will choose customer I if offered the assortment C. Admit Sora. Hmm? Oh, is he the professor at? Oh, okay. Okay. Cool. Welcome, Sora. Yeah. So we're gonna make some widely used assumption on the demand function. So the demand function is actually for supplier J, fj of c. It's just the probability that the supplier will choose any option if offered assortment C. So it's just the sum over all the probabilities in the assortment C. Or equivalently, just 1 minus the no purchase probability. Similarly, fi of s is the demand function for supplier I. We will assume that they are monotone and submodular. So monotonicity meaning that if you offer to a customer a bigger subset, right, then that would increase the probability that the customer will choose something from that set. So that's monotonicity. This is like a very reasonable assumption. Yes, 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 indeed. So if C is contained in A, fj of C is smaller than fj of A. And then we will assume as well that the demand function is a submodular. So submodular function, if you're familiar with that, so that the function that verify the diminishing return property, meaning that if you think about the marginal increase by adding an element to a set A, that marginal increase is actually larger for smaller sets A as compared to bigger set B. So monotonicity actually and submodularity are verified by all random utility choice models. So there is a class of choice model that is called RUM, random utility choice models. And every choice model that is within that class verify monotonicity and submodularity. So these are very standard assumption in the literature of choice modeling. If you're familiar with the choice models, is MNL choice model, multinomial logit model, mixture of multinomial nested logit. These are like large class of choice models that have been introduced in both economics and marketing, OM and OR. They all verify monotonicity and submodularity. So in this first model, we'll think about the unconstrained problem. So we're not going to put any constraint on the assortment in the sense you don't need to offer a fixed size, right? But in the paper, we have the extension as well to constrained assortment. And as I said at the beginning, if both users select each other, whoa. It was jumping. Did I click on some smart key? Okay, good. So as I said, if two users choose each other, then they will generate a match. The goal of the platform is to maximize the total expected number of matches. That's the objective function that we are focusing on. Just wanna. We started at 3:30. Yes, we have to. So again, one thing that I still haven't defined is how do the interaction happens. So what are the dynamics of the problem? As I said at the beginning, it will depend on the design of the platform. Yes, please.
Am I right? Okay, why I'm not right that monotonicity will imply that I want to show everyone? It increases the probability, right? The total probability.
Yeah. So if you just basically think about a single customer, just one customer, yes, you are right. The optimal solution is to offer everything because you don't have revenues. But if there are like many customers, there is
you want to match.
you know, yeah. If you offer everything, then maybe this guy will go to the popular option. The other guy will also go to the popular option. But that popular option only can be matched once, so that would not increase your total number of matches. Yeah. Good point. So now, thinking about the design of the platform, I want to ask the question: does the adaptivity matter in this type of problems? So let's start with a toy example. This is a toy example where I have about 2 customers and 1 supplier. Okay, so I have 2 customers and 1 supplier, and this is the choice model for the customers. So customer I will choose the supplier J with probability half, 1/2, and therefore will choose the no option with probability half. Okay. Same thing for customer I prime. So they have the same choice model. If you offer the supplier J, then customer I prime will choose it with probability 1/2, and will go to the no purchase option with probability half. On the other side, this is the choice model that I choose for supplier. So actually, we have only 1 supplier, just 1 supplier. Yeah, I should just remove the S. Yeah, so for supplier J, the choice model is as follow. So if you offer the subset C, so the probability that the supplier will choose an element from that C is 1/1 plus the cardinality of C. To put it in simple terms, if you offer only customer I, then the supplier will choose this customer with probability 1/2, and will leave with probability 1/2. Same thing for I prime. J will choose I prime with probability 1/2, and will leave with probability 1/2. Now, if you offer both customers to this supplier, then J will choose I with probability 1/3. So because the cardinality right now is 2, will choose I prime with probability 1/3, and would leave with probability 1/3. Okay? So this is the choice model of supplier. So let's study it. Yes, please. This one? No, so like basically, so the monotonicity is not on the probability, it's on the demand function. So the summation of this over the C, right, yeah. So it's 1 minus the, so actually if you offer 1 element, the demand function is half. If you offer 2 elements, the demand function is 2/3. Yeah. Good point. So let's study, as I said, 2 different policies. So the policy 1 is the following. So let's process all the agents at the same time. Processing agents at the same time, meaning we're going to offer them assortment simultaneously. So for I, we will offer J, because that's the only option. For I prime, we'll offer J, that's the only option, and J will see both I and I prime. But simultaneously, let's see what is the expected number of matches that we get here. So if we do that, the first policy, then, as I said, I will choose with probability half, leave with probability half. Same thing for I prime, and for J, we'll leave with probability 1/3, and we'll choose with probability 1/3, 1/3. What is the expected number of matches that we get here? Well, we get a match here with probability 1/6, and we get a match here with probability 1/6, so the sum of that is 1/3, okay? So the objective function in this toy example for policy 1 is 1/3, okay? The sum of the 2, yeah. Because this will happen with probability 1/6. So this is the expected number of matches. Yeah.
But I'm a little bit puzzled with the assumption you seem that the probability of match with this person independent, right, of each other.
The
So if I and J are offered, the probability that J was matched with I is 1/3, and G matched with I prime is also 1/3, and they're independent. There is no correlation. So
yeah.
something that, I mean, I would suppose in reality there should be correlation.
Are you so there are 2 things, 2 notion of independence. Are you telling me about the customer choices?
No.
Or like so this is a J basically. So there is a choice model that defines the distribution, right? It says that, you know, if you offer I and I prime, the J will choose I with probability 1/3, and J will choose I prime with probability 1/3, and will leave the market with the no purchase option with probability 1/3.
Yeah,
So
and what I suggested,
yeah.
probably in reality there should be some correlation.
Well, I mean, the correlation is by nature in the sense that, you know, it's the distribution that decide, you know, these are complement events. So it's just saying like, you know, I have these 3 choices and I will choose this with probability 1/3 and choose this with probability 1/3 and choose this with probability 1/3.
But my choice with probability 1/3, one doesn't influence the choice with probability 1/3. This is probabilities are independent.
Sure. There, yeah. You choose only one option. Yeah, 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 yeah. Yeah, yeah, yeah. Yeah. So the distribution is just like. No, 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 no. It's only one choice. Yeah, yeah, yeah. Yeah, yeah. There's only one choice. Yes, yes. Yeah, yeah, yeah. Sorry, I should have mentioned that. Yeah, 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 yeah. So the customers are independent. So every customers would come. You know, the choice of customer I is independent of customer I prime. Yeah. Yeah. Okay, so let's go to policy 2. Right now, let's process things adaptively. So in the sense, we will first process I and I prime, and then we will go to J. So for I and I prime, they have only one option. So we will gonna offer J first to I and I prime. These are their probabilities. And then, so here, based on the outcome, I will choose a different assortment in the second stage. Meaning, if only I choose J, then I will offer I to J. And J will choose I with probability 1/2 and will leave with probability 1/2. If same thing, if only I prime choose J, then there is no reason to offer I because there's not going to be a match there. I will only offer I prime. If both I and I prime choose J, then I will offer the assortment I and I prime to J. And then J would leave with probability 1/3, and we'll choose one of them with probability 1/3, 1/3. So in this case, we will get a match here. Conditional on I and I prime choose J, we'll get a match with probability 2/3. And on this here, like conditional on only I choosing J, we'll get a match with probability 1/2. So here, if, you know, I'm not showing the algebra, but if you compute the expected number of matches that you will get, you will find it is equal to 5/12 under this adaptive policy, which is strictly higher than 1/3 that we get in the static policy. And why this is the case? So because you for one side you're offering an assortment, you wait until you see the choices, the decision of one side before you offer to the other side, and you adapt what you offer to the other side based on the outcome of the first stage. Because if I prime did not choose J, it's gonna be a waste to offer I prime to J, right? Because that will only decrease the probability of the other one, right? It will decrease from 1/3, from 1/2 to 1/3, but without a benefit, because at the end of the day, even if J chooses back I prime, that would not be materialized to a match since I prime did not choose J. So adaptivity matters, right? If you process things in an adaptive way, you could generate more matching. And the question that we want to ask here is like, how much valuable is one type of policies over the other? Like, how much this adaptivity matter? And mathematically speaking, we're going to be interested in the notion of the adaptivity gap, which is the ratio of the objective function of two policies, the worst case ratio over all instances. And the second question is an algorithmic question. Given a policy, how can we solve the problem? How can we approximate or solve the problem? So I'm gonna skip the literature. I've just put some of the papers here on both assortments, optimization, and two-sided assortment. So I think this line of literature, I would say, started with paper of Itai Ashlagi and co-authors in 2020, and were a couple of papers that followed afterwards. But the main difference is our work focuses on like different platform design and studying the adaptivity gap, and also some new algorithmic results for some problems. So going back to my platform, to my model here. So this was the model. I will right now tell you about the policies that we consider, or the class of policies that we consider. But the first question, what is a policy? So a policy is the decision maker is going to decide what subset of user to select and what to offer them, okay? And in which order. So for instance, a policy might say like, I'm going to start with this customer, offer some subset of supplier, wait to see the outcome, and then go process the second customer or some other supplier. We will focus on these 4 main policies. The first one is fully static. What I mean by fully static, this is the most simple policy, is that you process everything simultaneously. You offer to all agents an assortment at the same time, and you let them choose, and if 2 agents choose each other, that's a match, okay? So that's the first policy. It's called fully static. One round. Yes, it's the first example, exactly, yes. Then the second policy, I will call it one-sided static policy. So in a one-sided static policy, you are going to do things in 2 rounds. In the first round, you're going to process customers, but simultaneously. All customers at the same time, you're going to offer them some assortment. Then you will see their choices, and then you will offer to the supplier simultaneously some assortment. Actually, customers, yes. No, that is going to come from some optimization problem. Simultaneously to each a subset. They're not the same. Yes, the same is a feasible solution. It might not be the best thing. They can be different. Yes. I see where they choose, and then I offer for that's the example 2 that I've shown. So yes, and one thing that I want to mention here, so in the toy example that I've shown you was simple because there was only one customer on the other side, you know. But right now you have one supplier on this side. Now you have many suppliers, so you might offer to this guy a subset, to the other guy another subset, right? Because they have different choice models. It's a heterogeneous market. If you notice something here, the second stage problem is simple, because what you will do for each supplier, let me ask that question, like what would you do for the second stage? Imagine you offer an assortment to each customer, and they choose, right? So the choices are given to you. Each customer made the choice, might have choose one supplier, or might have left the market. Can you do it one? No, I'm saying for the second stage. Yes. Yes. Exactly. Yes. Exactly. All the people that have chosen you, because of monotonicity and because the choices are going to be disjoint, right? Because you can only choose once. So if you think about the graph from this side, it's going to be like disjoint. This guy, it's a partition over all the customers. So second stage is a simple problem. The difficulty of the mathematical problem is what would you offer in the first stage to each one of them. And this model has been studied. This was the first model in this paper by a couple of Stanford Fox. So here you can do the same thing. You can start with also suppliers and customers would respond. This is, and when I say OS, that's the max out of these two policies, whether you start from customers, supplier response, or the other way. Yes.
Like in the business of Uber is kind of right, like matching transportations and by region.
So you can think here about, but the choice of the customers are, so in transportation, indeed, right now, like drivers can also, yeah, but I wouldn't say ride sharing is the best example here, because in ride sharing, so far drivers don't get an assortment to choose from. They get like requests one by one. So the platform kind of like does not decide, like tell the driver, hey, by the way, you can either.
Not in a drive. In a drive, they can see all the customers' requests, and they can pick the best.
Okay, so then that's good. I don't use I don't use InDrive. I use Uber, and actually I worked with at Uber Marketplace, and yeah. So the model there is that the customer see like a request, and then you do yes or no. But if you know, does the customer also see an assortment of drivers? So then, yeah, it's a two-sided assortment platform. Maybe we should do some collaboration with InDrive, if they're legal, by the way. Very good question. So the question has been studied in the literature, where you should start from. Does it depend on, you know, just the numbers? That's only one factor. Actually, the most important factor is, does the choice model is such that those customers are picky or not? And what I mean by picky, meaning that they have high probability, if a picky customer that has high probability of leaving the market, right? So then you would likely want to start with the picky customers. You offer them something, and then the other ones that are non-picky, they will respond, because the other ones will choose something with high probability. So that's the general intuition that would come up from the algorithms that I will describe in a bit. Another policy is one-sided adaptive. So let me go here. One-sided adaptive. What I mean by one-sided adaptive, you are going to start from one side, but you are going to process customers simultaneously. Sorry, not simultaneously, sequentially. Meaning that you're going to start with one customer, offer an assortment, observe the choice of the customer, go to another customer, and so on and so forth. So you do things not simultaneously, but in an adaptive way. And then after that, suppliers respond. Suppliers respond simultaneously or not, it's the same thing, because again, you're gonna get a partition of choices, and the second stage problem is simple. One-sided, you can also do the other way. So you start from suppliers, you process them sequentially, and then customer respond, and the max out of these two policies is what I call POA. Yes?
Do customers see the previous choices?
The customer or the platform?
No, the customer. If I'm number 2, do I see what the first person behavior?
Not necessarily, but like that's not gonna change your.
Oh, because I'm not choosing.
Yeah.
So, I'm not choosing, right?
So the customer first comes and choose something, right? The second customer would come, right? Would choose something independently of customer one.
But my choice is the whole set.
Yeah. You can choose the same person if you want, because that person haven't made the choice yet, right? So let's say basically there is a bunch of freelancer, we are customer, and I come here and I says like the platforms offer me this assortment, and I choose you as the freelancer that want to work on my project. Then there is another customer, the platform might show you again to that customer, and the customer might choose you again, and then we are what we call the backlog that you will be offered at the end, and you will choose your single choice, and that would be the match. Okay?
No, I understand, but maybe, again, it's not clear. This is the best possible one-sided adaptive policy. Maybe it would be the good for the first one, choose among all. The choice for the second one, I restrict you.
Oh, yeah. So that's. Oh yeah, I'm not saying to offer everything. So you're gonna offer an assortment. That assortment is gonna be decided by an optimization problem. Yes. Yes. Yes.
sometimes customer will think this supplier is high quality, so then maybe this customer also chooses this supplier, and then this breaks the independence.
Yes, we are assuming that the customers are independent, that they make their choice independent of the other, and the platform doesn't even show what the other customer choose. But what you suggested is another line where there is one paper on that, on like, it's kind of like introduce competition and signaling between customers. It's a very nice paper on that I can show. Best and Yuri have a nice paper on this model. So let's say the last one is the fully adaptive model. In the fully adaptive model, you can process agents in any order. Meaning you can start with the customer, go to a supplier, go to another customer, and for each one of them you're offering an assortment, right? And it is clear that this is the most flexible policy. So these policies are nested. In the sense, fully static can be simulated using OS, and OS is subset of OA, and OA is a subset of FA. So this is like these are like the four, I would say, classes, and you can think about many other policies that could fall in between fully static and fully adaptive. Any question about the policies? This is the time left. Okay, I got gotta be a bit quick. So since these policies are nested, it is clear that the highest number of matches can be achieved by fully adaptive, and the smallest one is fully static. So we are interested in the first question, as I said, the adaptivity gap. What is the adaptivity gap? Is the ratio between the optimal objective function of two policies. So it's the minimum over all instances. If you take two policies that are nested, pi and pi prime, it's the minimum over all instances of opt of pi over opt of pi prime. Meaning if this ratio is equal to 1, then there is no benefit of adaptivity. The policies would achieve the same objective function. If it is smaller than 1, there is some benefit, and we want to understand whether this benefit is constant, is it bounded, can be unbounded. That is the first question. So this slide will have all our results. So if you're not paying attention, this is like the slide, please. Yes, all possible instances. And its preferences. The choice model is a preference. Yes. Yeah. So
I can choose 1, 2, 3, 4, 5, or 5 to 3 to 1. You minimize all these policies, right? Because
this is the object. This is the optimal. This is the optimal. Yes. Yeah.
But optimal
for a given policy.
No, for given preferences or for all preferences.
So I give you a choice model. An instance is given by a choice model. Choice model would be like, this is the distribution of probability, right? And the number of customers and the number of suppliers. And M and the function phi I for all agents I. This is one instance, right? You're gonna solve for that instance. You're gonna get the optimal for that instance, right? So the minimum over all instances, meaning like for any value of n, for any value of m, for any preference function, right? What is the worst case ratio here? The optimum is a function of instance. If you wanna like write it mathematically, it's gonna be all instances I, opt pi of I, opt pi prime of I. Okay? Yes. Yes. So this slide is going to, summarize all the results, or the main results in the paper, and then depending on the time, I might go deep into explaining one or two results in more depth. So in the bottom, I'm gonna write the adaptivity gaps. Okay. So the adaptivity gap between fully static and one-sided static is big O of 1 over n, where n, think about it as the number of agents that you have in your graph. So this is saying that actually the gap can be arbitrarily unbounded between fully static and one-sided static. Just by introducing, going from 1 round to 2 rounds, you might gain a lot. If you know, the difference between, you know, fully static, if you recall, is processing everything simultaneously, and one-sided static is round 1, process one side, and then go to round 2. Okay? So that's the first example. And the way how you show this is just by an example. Construct an example where, you know, the gap can be arbitrarily unbounded. Then the second result is we show that it is a constant, the adaptivity gap between one-sided static and one-sided adaptive. The constant is 1 minus 1 over E, and it is tight. Meaning that there exists an example where the gap exactly between one-sided static and OA is 1 minus 1 over E, and you can never be bad than a fraction of 63 or 67? 63, yes. It was written here, I think it was your. So we use some techniques on, you know, the correlation gap of some modular function to show this result with some Nabel LP relaxation of this OA. I'll see if I'm gonna go into one of the results in details, but let's see which one depending on the time. Let me first list all the results. Then the gap between OA and FA is half, 1 over 2, okay? So, and again, this is tight. There exists an instance where the exact gap between OA and FA is 1 over 2. So the conclusion here is, you know, from one-sided static to fully adaptive. And of course, there are many other policies that you can think that are in between. Yeah. Were you the AE for this paper? No, because that's exactly the question of the reviewer. So the gap. So we have. It's a natural question, yeah. So we show in the revision that the gap is actually 1/2 times 1 minus 1 over E. It is exact. So actually, the lower bound is, by definition, like 1/2 times 1 minus 1 E was like, can you find an instance where the gap is exactly, yeah. So we found a gap that asymptotically converges to 1/2 times 1 minus 1 over E, yeah. And it is in the paper already on archive, yes. So what we said is like from OS to FA, you know, the gap is constant, right? So just like introducing this one level of adaptivity, you know, you gain a lot, of course, in the worst case. And from OS to FA, it's a constant. So there was some question, yes? This is any number of customers and any. Well, this is the worst case gaps if you have 2 by 2, but the instance to achieve 1 minus 1 over E, you might not achieve it with 2 by 2.
Oh, that was my question. So for different ends, the gap can be different. You might not achieve this.
Yeah. So the 1 minus as a lower bound, this is true for
no, but
yeah.
Some finite n where it achieves, or it's achieved this gap in infinite whenever you make.
There exists n and m such that, and an instance and a choice model such that OS will basically and the gap between OS and OA will be 1 minus 1 over E. That's one lemma. The other lemma is for any n, for any m, for any choice function, the gap cannot be worse than 1 minus 1 over E. Okay? Yes. So if you introduce IIA, independence of irrelevant alternative, no, you can still show that it is 1 over n. Yeah, actually. So MNL is I. So the multinomial logits model suffers from IIA. The nested logits model does not suffer from IIA. So even with the multinomial logits model, you can construct. Actually, I might have a slide for this. I don't have too much time, but yeah, I answered, I think, the question. Yeah. So algorithms. Alfredo Torrico and Andrea Lodi and Margarita Carvalho, they showed 1 minus 1 over E approximation for OS. There exists an algorithm that achieves 1 minus 1. So this is how to solve the problem, right? Because you need to offer an assortment. The number of assortments, you know, that's exponential, 2 to the n subset. So the problems are NP hard in general. You need like an approximation for the problem. Actually, the first approximation for this was like some very small constant, and the state of the art is 1 minus 1. And actually, you cannot do better than 1 minus 1 over E. But we contributed to the rest of the literature by adding, by solving OA. So we have an approximation of 1 over 2, and using some greedy type algorithm and some primal dual analysis. This 1 over 4 is just a byproduct of this and this. So if you basically use the same algorithm for OA, it gets you half approximation for this. And because this is not more than half of this, it gets you 1 over 4 for fully adaptive. And this one, we solve it only for MNL, the multinomial logit models. This is the fully static. The best constant that we have is 0.067. It definitely can be improved. I invite you to think about this problem if you like working on algorithms. So, yes, please. Yes. So, okay. So, good, very good. Thanks. So, good, very good point. So, one thing that I want to mention, except this result, all the results apply for random utility models. So I'm not making any assumption on the choice model. I mean, except monotonous submodel, which are verified by any random. So, meaning that the customers want to maximize its utility, right? So, in the sense that you offer an assortment, then basically based on what you display to the customer, they want to maximize their utility. So they will choose the option that maximizes their utility. Now there is one paper that's kind of introduced like some sort of signaling and competition in this. Maybe they don't want to, because they know that this is a popular option and it might be taken, so I should not choose this one and choose something else. So then you are changing the choice model. It's not a RUM thing. There's one paper that's looked to some model, but achieving, like I would say, algorithmic results, they're going to be like model dependent. It is going to be hard. So, but this is a very good, question. And so the paper is called Signaling Competition in Two-Sided Market. Yeah. But it's not algorithmic, it's merely an empirical paper. Yes, Reda. 10 minutes, yes. Okay. So let me give maybe 10 minutes, okay, 5 minutes about one result and 5 minutes about another result. The most simplest result is the big O of 1 over n between fully static and one-sided adaptive. The example is the following. So think about it. In a market, there is unbalance where you have one customer on one side and n supplier on the other side. The probability, these suppliers are very picky. They will choose this customer with probability 1 over n, and they will leave the market with probability 1 minus 1 over n. That's the choice model in this instance. On the other side, this customer is not picky at all. Whatever assortment you're going to offer to that customer, the customer will choose with uniform probability. If you offer only one option, the customer will choose it probability 1. If you offer two options, the customer will choose it probability 1 over 2, 1 over 2. Okay? So what does fully static does here? So fully static, you take this customer and you take a subset of supplier. Maybe all of them, maybe any subset. Let's just say C. C could be any of them, could be just a subset of them. What's the objective function? Well, you're going to have like each edge will, the probability that it will be a match is 1 over n on this side, and then 1 over the cardinality of the set on the other thing. And then how many edges, because it's the cardinality of the subset that I choose. So it's 1 over n times 1 over c times c, so it's just 1 over n. So the probability that, the expected number of matches that you will get here if you offer things simultaneously is 1 over n. However, the right thing to do here is you want to start with the supplier choosing before the customer choose. Customer is not picky at all. But if you offer things simultaneously, customer 1 might go to supplier 1 and then was chosen by supplier 2. At the end, you don't get any matches. So in one-sided static, in this example, if you basically process the suppliers, what's the probability that you get a match? Well, think about the complement event. What's the probability that you don't get a match? You don't get a match if none of them chooses. So if none of them chooses, that will happen with probability 1 minus 1 over n to the n, right? And you will get a match with the complement probability 1 minus 1 over n to the n. As n gets large, this converges to 1 minus 1 over e. So the expected number of matches under the one-sided static policy is a constant. The fully static is 1 over n, so the gap is arbitrarily bad. It scales with n in this example. Okay, so this is example so this is gonna get a bit more technical. Let me, this is to show the gap between OS and OA, the one-sided static and one-sided adaptive. So if you remember, this was the second class of policy. This is the last one. Just to give you very high-level idea about what we will do here. So the technical ingredient is to come up with an LP relaxation. So this is an LP relaxation for the problem. So this relaxation has an exponential number of variables. I'm not going to solve it to construct an algorithm. This is just to show that the gap is bounded here between OS and OA. We will use the notion of correlation gap. So and this notion is based on the fact that fj, the function that we have here, are submodular. So the correlation gap of a submodular function is a worst case gap between any distribution, the multilinear relaxation of submodular function for any distribution, and the independent distribution. An independent distribution actually will be a feasible static, a one-sided static solution, and we know from a paper that appeared 15 years ago that this correlation gap is actually 1 minus 1 over e, and we will use that result and come up with a lower bound, 1 minus 1 over e, and then we show an instance in the paper where the gap is exactly 1 minus 1 over e. The proof, or the high-level proof for idea for the last result, the half gap, is based on some correlation gap, some correlation argument between, some coupling arguments. We're gonna couple a fully static policy with a one-sided adaptive, a fully adaptive policy with a one-sided adaptive policy. So let me skip those details here and maybe talk about the greedy algorithm in 4 minutes. Yes. So one of our contribution is to find an algorithm for the one-sided adaptive problem. So meaning that you're gonna process customers sequentially and then offer them an assortment. What's the best thing so you can do? So we show that greedy is a very natural algorithm for this problem. And we call it random greedy because we just generate any permutation of customers uniformly. And then we offer greedily an assortment of suppliers. Greedily is just based on the final objective function. You will update the backlog of each supplier. The backlog will indicate how much this supplier will contribute to the overall function. I know I'm going fast here, but I'm just, you know, giving some super high-level ideas about how this algorithm works, and we show that this algorithm actually achieve 1/2 approximation, though I know, and my co-author know that we could improve this to 1 - 1/e. It's not on the paper yet, but we have the proof. Yes. Yes. So we know. No, this is like fix the problem, the one-sided adaptive problem. Of the optimal of one-sided adaptive, of that policy, yes. So the lower bound is 1 - you cannot have an algorithm, there is a hardness lower bound there. You cannot do better than 1 - 1/e. Yes, we do 1/2 of that instance. Yes, that's what this algorithm does. But I'm saying we can also do 0.67 of that instance as well. And that's the best thing you could achieve, yeah. More 1 - 1/e. Of the instance itself, yes. So let me skip here. So this was the summary.
For in your column, this is the one is online, other one is fixed.
So
About the full online?
yes, so I have the picture here. So this was known 1 - 1/e. We can do half here. That's what we have in the paper, though we improved recently to 1 - 1/e. For this, we don't have an algorithm for that. We are just using the algorithm for 1 because we know that the gap is half. This algorithm would also guarantee 1/4. Yes. And for this, we have it only for one choice model for the MNL. This is a static problem. This is just like a quadratic problem with fractional objective function, right? So there is no adaptivity here. What's next? So we do have as well more results for the cardinality case. When you add constraints on the cardinality, that would break submodularity in general of the demand function. So we lose in some constant, but it's still like we still have constant approximation and constant adaptivity gap, but they are worse than the case of the unconstrained problem. So some conclusions, takeaways. Yeah. So fully static policies are not good in the worst case. We've seen that they can achieve the lowest number of expected matches as compared to the rest. But this is in the worst case. Empirically, I mean, they're not the best, but then, you know, the gap, if you basically, the empirical gap is not as bad as 1/n in general. One-sided static policy seems to be very powerful and like kind of easy to implement as compared to fully static, where you have to wait for every agent to make choices before you choose the next agent and you process the agent. And as you know, you've seen in this brief introduction, but the algorithm, each class of problems comes with own challenges and in terms of approximation. We do have as well another paper that we released a few months ago on when you add revenue, like how do you design algorithms. And there's still a lot of rich problems actually to look at in this literature of two-sided assortment optimization. Thank you so much for your attention. Thank you so much, guys.